Okay, where is it? Ah, I can do this. Okay, so this is this next section is all about chemical thermodynamics. Chemical energy and thermodynamics. I'll try to keep my notes off to the side here so that you can see how I work out problems, and make some jots along the way, and I'll, if possible, scan these and have them available for you offline. So this particular chapter is one of the more potentially confusing and conceptual chapters that you'll encounter in general chemistry. And the reason is because we're going to talk about chemical thermodynamics, and which means we need to talk about chemical energy, introduce some concepts that are a little bit confusing and maybe not necessarily obvious, such as enthalpy and various sources of energy and different ways that chemical energy can be transformed into different kind of things. And in chemistry in particular, the concept of energy and thermodynamics is very central, because we need to know, does a chemical reaction have enough energy to occur? How is energy distributed amongst different degrees of freedom in the molecule, and whether or not a reaction itself will be spontaneous or at equilibrium or not spontaneous, or give off too much heat, not enough heat. What do I need to do to make this chemical reaction work or not work? So, to be specific, energy is the capacity of a substance. It is how much currency, if you would, does a substance or object have to move and do something. And for example, this energy can be in the form of the energy of motion. So energy of motion, which is called kinetic energy. And it has a formula called K, 1/2 mass times velocity squared. So the faster something is moving, the more kinetic energy it has. And you also have the energy of position or location. For example, if I have a particle, a substance here, like a ball of some mass m, and it's sitting on top of a hill, and it's rolling, it has an energy at 2 points. It has an energy here. Let's call this distance height. Okay, its energy, potential energy, is equal to v, and we'll call this of h, the height, is equal to mass times the gravitational constant times how high that object is. And as I move this object up and down, I transfer energy of location to the energy of motion. And one of the rules of classical mechanics is that energy is conserved, and that is that the energy is always constant. It's equal to 1/2 mass times velocity squared. You can't see that. Okay. Plus the potential energy. Let's say how high I am above that hill. And so this is the kinetic energy and the potential energy. And molecules have kinetic energy and potential energies as well. And the law of conservation of energy is that energy can be converted between different forms, in this case potential energy and motion, kinetic energy. Or it can add heat. In this particular case, there is no heat that's added to the system, and so on. Okay, so energy generally is a conserved quantity. This statement that the total energy content of the universe is constant is a falsehood. It's the total mass energy of the universe is possibly constant, and this is of deeper philosophical, cosmological significance for purposes of classical kinetic energy and classical type systems. Energy is a constant. It's energy of a system, energy of a closed system is held constant. So in other words, if I have a box and I have it perfectly insulated from the environment, I have a particle ricocheting around in this box. The energy of that particle is constant. So energy for a closed system energy is constant. Total energy is constant. Okay. If we were to write this in terms of a calculus equation, we would write something that energy dE dt is equal to 0 in terms of how we would write this as a rate. The energy has no rate of change. Okay. So again, potential energy is important. So if you remember when we were talking about the electron and the proton, you have a proton here and an electron here. I had a potential V of R, and this is the distance between here and here. So V of R, in this case, was equal to, it was attractive, minus, I had a net positive charge here, Z of E, and a net negative charge of E. So minus Z E squared over R, and because I'm using SI units, 4 pi epsilon naught, is the Coulomb energy of an electron, this electron being attracted to that nucleus. And it also has kinetic energy, and the kinetic energy, Ke, again using their notation, 1/2 mass times velocity squared. It's the same. It doesn't matter if we're talking about a ball rolling down the hill, or if we're talking about a classically described electron. Its kinetic energy is the square of the velocity times 1/2 the mass. Okay, and this is basic laws of physics. And as the electron, if it was a classical electron moving about this central potential, I would have a balancing between the kinetic energy and this, and of course the total energy of an electron, if you remember, is quantized, and but it's a constant. Again, energy is constant. Okay, and again, and going back to my picture that I have over here, we have this idea that if I hold this little mass ball in place here at A, and I let it roll down here to B, I have a change in the energy. I have a change in the potential energy. So rolling down the hill to B changes my potential, but by whatever the height distance between A and B happen to be, and from that I can then calculate the velocity. How fast is this ball rolling as I go down this hill? Okay, and the higher I put it, the more energy I have, and I can trade energy back and forth. Now, in the presence of friction, if I have friction, energy is not conserved. So energy of the object decreases in time. okay, due to the friction, because I'm slowing it down. The velocity is being dragged by the system. And where does that energy go? The energy is going into the heat of the object and into the heat of the surroundings, and that that frictional energy, the total energy is still conserved, but that energy is now being dissipated amongst all the different degrees of freedom that I happen to have in everywhere. It's an irreversible problem. You probably have never seen the case where a ball sitting at the bottom of the hill suddenly flies up the hill because you happen to heat it up a little bit. That never happens. So in thermodynamics, we have the concept of heat and temperature. So it's important to distinguish the difference between heat and temperature. Temperature in the thermodynamic sense is really a measure as an average kinetic energy of all the particles in the object. Okay, and so it's a measure of, you know, how much motion is going on in the object of that, in the atoms of that object. So even if you have a system that's at rest, you know, if I have, for example, atoms that are connected to each other, atoms by little springs, okay, and these are atoms connected, you know, to each other by, you know, keep going out, you know, going out. So these are my atoms. They are in constant motion. They're moving back and forth and left and right and potentially up and down at some average kinetic energy. The fact that they're moving back and forth, back and forth, back and forth, back and forth, left and right, up and down, they are in constant motion, even though they are being held in place by the relative positions of all of the other atoms. Here's another atom right there. And maybe you have another atom right there. Some springs in between, and these atoms are moving about, and but still locked in place. But they're moving back and forth about their equilibrium position. Okay, the temperature difference means that I've increased the amount of kinetic energy in each particle on average. So some may be a little hotter, but on average, it's a measure of the kinetic energy. So heat is a measure of the transfer of energy between one object and another. So heat means I've transferred is a transfer of so it depends upon a temperature difference. And one of the things that we'll learn in thermodynamics is that heat flows from something hot to something cold. You never go from taking energy from a cold object and putting it into a hot object. This is a spontaneous process and is a consequence of the laws of thermodynamics. Heat flows from hot to cold and never from cold to hot. It requires work to take something cold and make it, and to transfer the energy from something cold to the heat. Then if you want an example of this, look at your air conditioning bill. Inside of your house, you have a nice cool house, and outside is hot, humid Houston. And if I want to move energy from my cooler house to the outside. I have an air conditioner, and I do work. I do work to move energy, to extract energy, even more energy from the cold, to dump it out into the hot. However, if I turn my air conditioner off, I spontaneously will have heat flow from the outside to the inside. Okay? Now, we just use two different words. So we use work. So if I want to go this way, work is required to push myself in that direction. Heat will flow in this direction, but I need to do work, or maybe I can extract work by having something hot to something cold. So we have two different concepts that are incredibly important in chemical thermodynamics: the concept of heat and work. Okay, now thermodynamics, now both of these are path-dependent properties. And in the case of energy, the total energy is independent of the pathway. So for example, if I go back to my ball on the hill, because I have energy moving from one form to the other form, one form to the other form, it's a constant of the motion. The energy that I have at that position does not depend upon how I manage to get there. It is simply E is a function of the position and the velocity. Okay, it is simply I'm at position X and I'm moving with velocity V. It's a independent path, only depends upon where I happen to be. Heat, however, and work depend upon the pathway. And you can think about it, in all sorts of different kind of ways. If you take a very circuitous route to get to your home, you will require more gasoline, and you require more work to do so. However, if you take a shortcut, you will take less work, and your total energy will be the total energy difference will be the same, because maybe you've moved uphill. For example, if I'm moving, if I'm a mountain climber and here's my hill, and I try to walk straight up the hill, it requires a lot of work. But if I take a route like this, it might take longer. I get to the same point. My change in energy is the same, but I used a different amount of work to just go straight up the hill versus taking this sort of side to side to side to side switchback type approach. So in thermodynamics, energy is what's called a state function. And heat and work are not state functions. They depend upon path. They are properties of change. The work that you do on a system is the energy that you've added or removed from a system by performing work on it. You've pushed it, you've compressed it, you've done work on the system. Heat is how much energy you've added by heating it up or cooling it down. Okay? So again, a state function depends only upon where you are. If I'm sitting right there, that's my state. If I'm sitting right there moving at some velocity, I have a state. That's described by the velocity and the position. And what's important to know that the energy difference between here and here is the same as if I were to move this way versus it moving around the mountain, do all sorts of crazy things. The energy difference is simply that I move from this height or this height to that height. It simply is a function of position and where I happen to be. It does not depend upon the pathway. These depend upon path. Okay? So, in a system of chemical energy, what we have is the following. Typically, we have the following scenario. We have a vessel that has stuff in it, and we have everything else. Okay, this is the surroundings. And this is our system. Okay? Now, generally, if we have a change in the system, various things can happen. I can have the system could heat up as a result of a chemical reaction. The system can expand as a part of a chemical reaction or some sort of change. And we refer to the following. So if the system heats up, or maybe a better way to put it is that if I have heat flows from the system to the environment, this is called exothermic. Okay, exo, like exiting. Heat flows out of the system. And the opposite of that is if heat flows into. Okay, so for example, maybe your chemical reaction caused the system to cool. Okay, that's called endothermic. Okay, exo, exit, endo, it's for entrance, if you want to think about it, in sort of the derivation of the word. If heat flows into, it's entering the system, exiting, exothermic. Okay, some very important terminology that we need to have for this. Now, in a typical chemical reaction, you have reactants and products that might start off in the system. Maybe I have A plus B going to C inside of my system, okay? And maybe the energy of A plus B is greater than the chemical energy of system C, and that energy needs to go someplace, and is dumped into the surroundings. That is called an exothermic reaction. Maybe it's the other way around. Maybe the energy of C is greater than the energy of the reactants. In other words, I need to heat the system up, light it on fire, add energy. Heat flows into the system as an endothermic reaction. It requires energy in the form of heat to initiate the chemical reaction. Okay? So we have endothermic reactions that you have to add energy to, and exothermic energy reactions which energy is given off. Some reactions are very exothermic reactions. Explosions are very exothermic. For example, adding acid to water is an exothermic reaction because it's releasing energy by breaking apart, by combining, doing some sort of chemical process, is releasing energy into the system. The system responds by heating up, or the surroundings respond by heating up. Heat flows from the system into the surroundings is an exothermic process. Okay, so again, this is just a picture that sort of illustrates this again. I have a change in the potential energy between the reactants and the products. In reality, what we would really look at this isn't so much the change in potential energy, but rather what's called the change in the enthalpy, or the change in the total energy of the system, depending upon whether or not the system is in constant pressure or in constant volume. And then that distinction will be made more apparent when we dig deeper into thermodynamics. Most chemical reactions occur under the conditions of constant pressure. So really what we will talk about instead of potential energy of the system will be the difference in enthalpy. And we'll talk about what enthalpy is very, very soon. So if you look at the enthalpy is another state function. It's similar to the energy, but it's a state function. And so the reactants have enthalpy, the products have enthalpy, and the difference between the enthalpy of the reactants, or the products and the reactants, products minus reactants, is the enthalpy released, the heat released into the system, or it could be the other way around, in the case of an endothermic reaction, where you have to add energy into the system for that system to go. Okay. Now, this is sort of a question that we may not be aware of. Freezing of water, is it endothermic or exothermic? You may wonder. Okay, so if I have water at 0 degrees Celsius, liquid water at 0 degrees Celsius, and I allow it to do its thing, it will form into ice, because that's the freezing point of ice. However, what drives that process is two things. One, you're first of all, you're going to a more ordered state, and second of all, so you would think I would take energy to put myself into that more ordered state. Or maybe I would release energy. So in fact, that's exactly what goes on. I release energy. Energy is released going from the liquid state to the more crystalline state. And so consequently, energy is given off. This is called the latent heat of freezing. And it's a small amount of heat that's radiated away when systems start to freeze. We don't experience this very often in Houston. It does snow in other parts of the world, and where I grew up, it snowed a lot. And what you would notice is right before it started to freeze, or right before it started to snow, it would warm up. You could feel it a little bit warmer, and suddenly it would start to snow. And that was all of this latent heat of freezing that was being released from the water vapor in the air, forming into snowflakes and condensing into snow. And so it would warm up just a little bit, not much. Okay? So, again, we can look at this as endothermic or exothermic. It's really more of an issue of heat flows rather than, so a person's hand becomes cold upon touching the ice, which is the system and which is the surroundings. It depends upon which, your viewpoint. Is it exothermic for your hand? If you put your hand on ice and that's your system, heat is flowing from your warm hand into the cold ice, and so that's exothermic. The ice gets warmer, so it's endothermic with respect to the ice. And the same way with water boiling on a kettle, and that is, it is pulling heat in. That heat is flowing into the water. And likewise, water vapor, when it condenses in a pipe, energy is leaving and forming the energy of condensation. As it condenses, energy is released, exothermic. And when ice cream melts, again, heat is flowing into the ice cream and from the environment, and that is then an endothermic process. The system is getting warmer. It's receiving energy from the environment. Okay, so again, you can think about whether or not something heats up or not by is it exothermic or endothermic, and these are all, for example, so methane burning is clearly an exothermic process. The combustion of methane produces heat, light, and a lot of other things. And when water drops on skin evaporate, this is the process of evaporative cooling. And again, heat is flowing from you into the water droplet, leaving you to feel cooler. So it's an endothermic. It's exothermic for you and endothermic for the water droplet, I guess. Okay. So, we can look at this particular case. Hydrogen and oxygen gas, if you were to mix them together, They don't do anything. You can have a bottle of oxygen and a bottle and a mixture of oxygen and hydrogen, very very stable. Doesn't do anything. But you put a spark in that, you you activate. You definitely release an awful lot of energy in this explosion, and so it is violently exothermic. So consequently, the mixture of hydrogen and oxygen is at a much higher chemical energy state than water. So if you combust hydrogen and oxygen, you form water. Let me write this down perhaps. So H2 plus okay, plus a lot of heat. Okay, a lot of heat is given off in that particular reaction, and that's an exothermic. It's an exothermic reaction. If I wanted to write this out in terms of like the enthalpy, or maybe an energy diagram, I would have something that would look like 2H2O, 2H2 plus O2 up here at some energy, and I would have H2O, two H2Os. And this energy difference would be the energy released as heat, the enthalpy, which will eventually denote as H, heat. The enthalpy is just an 8. These are all in the gas phase. Okay, and this is probably water vapor in the water vapor phase. The other reason this is so explosive is because you've also drastically heated the system up, and when you heat a gas, it expands. Okay, so the first law of thermodynamics. So thermodynamics has 3 laws. The first law is the conservation of energy. Okay, if you want to put it into the system, the energy of the universe is held constant. In other words, the energy of a closed system is conserved. It does not change. And the internal energy and in chemical thermodynamics, we usually denote that as U, as the internal energy of the system is the sum of all of the kinetic energies and all of the potential energies of all of the particles in the system. Take all the electrons, all the nuclei, all their different kinds of motions, you add all that together, and you get the total internal energy of the system. Now, that's a hard quantity to measure. We don't ever measure that quantity exactly. Usually we look at the average internal energy or the average kinetic energy of the system. And like I said before, the temperature of the system for an ideal gas, depends upon the system, is related to the average of the kinetic energy of the system. That little bracket means take an average. So on the time average, if you want, of the kinetic energy of the system. Okay. Now, this equation that we have here is one that you need to pay attention to. Okay, because thermodynamics deals with the changes of energy, the change of energy of the system. Okay, and the way that I can change the energy of the system, delta E, is I can add heat to it, or I can do work on it. Now, I've emphasized on the slide on, okay? So Q, heat added, and work W plus W is the work on the system. Okay, so for example, if I have something and I compress it, I will have done work on the system. Now, you might see this equation written in a different way, and that is in the following way. Delta E is equal to Q minus W. In this particular case, that minus sign says this is work done by the system. Okay, the work done by the system. Now, it's sort of like, and it gets confusing, and I realize it. And it's simply, you have to pay attention to the syntax. Work done on the system, work done by the system. Changes the sign. So if you want to think about it in the following way, the joke is that that Chuck Norris doesn't do push-ups. Chuck Norris pushes the earth away from him. In both cases, the change in energy is the same, right? The initial state, the final state is the same, but it depends upon your perspective. Did Chuck Norris push himself up, or did he push the world away? It depends upon your perspective. But you need to pay attention to the way things are worded, because if you say calculate the work done on the system, or I did 5 joules of work on the system, the energy of the system increases. If, on the other hand, the system does 5 joules of work on you, its energy decreases, hence the negative sign, because it lost energy doing work on you. So work, the difference between heat and work is the following. Work is the change in energy due to mechanical type processes. In the case of thermodynamics, it's pressure volume work. So generally in chemical thermodynamics, work is equal to minus P times delta V. Okay, the pressure times delta V. So this is pressure volume work. There's different kinds of work I can do on the system, different ways I can add and remove energy onto the system. I can put strain on the system. I can do different kinds of systems. But for the most part, the kind of process that we look at are what's called pressure volume work. So I have heat and pressure volume work are the two kinds of systems. So pressure volume work corresponds to the following case. If I have a piston, here's my surroundings, here's my piston, okay, and I push on the piston, I have some sort of gas on the inside of this piston. I do work on the gas. Here's my system inside of there. I'm doing work. I'm doing work on the system. Its energy increases because I've done work on the system to compress the system. I had to do work on the system. On the other hand, I could look at it the other way. Maybe I have an expansion of the gas and the system doesn't work on me. Energy is decreased because I've done work done by the system. It is decreased. I've added. Now the reason this is important is because you see in one case, remember volume change is always going to be, so delta V is always volume final minus volume initial, right? So in one case, if I'm compressing to go from a large initial volume to small final volume, delta V is going to be a negative number. Work is going to be a positive, and you could ask, I added heat to the system. On the other hand, if I have something that's very compressed, and I allow the system to expand, my initial volume is small, my final volume is large. This is a positive number. Delta V work is a negative number. Pressure is always constant. In this case, pressure is constant, maybe due to some pressure on the outside here. I removed heat from the system, but you see I get the sign right. So I always get this thing right if I calculate work as P minus delta V. And if we were to write this in more formal thermodynamics, we would write this as a dW as equal to P minus P dV, okay, and as a proper thermodynamic differential, and these are inexact differentials, which is again a mathematical concept referring to the fact that the work that I do depends upon the pathway that I take. Now, if I do this again on the other side, I be careful. So work done on the system, work done by the system, is Q minus W, and really the only difference between is where I put the negative sign here. Okay. And different textbooks will define this in different ways, and you simply have to be aware of that. And I'm pointing that out because it's an easy thing to get tripped up on. But the key is to always remember how should my energy change? Did I increase? Did I do work on the system, or did the system do work on me? Okay, if the work is done by the system, I remove it. If it's the other way around, my energy increases or should decrease depending upon did I work or does the system work? Am I getting work out of it? Am I getting energy out of the system by some sort of mechanical motion? Okay, so the sign, as you just guessed, is extremely important. Sign matters. Okay, so the sign, so Q again, Q is again a change in something. And again, if I were to be really, really careful, I would write this as a dq or a delta Q. That's right, as a delta Q. Some people will write this as a delta Q, but really it's a quantity that's changed. So Q is an integrated quantity. dq is the differential Q. But Q can be positive or negative. Okay? Or maybe I should write it like this. I can have Q as greater than 0, or Q can be less than 0. If Q is greater than 0, this is an exothermic. Okay, an endothermic process. Heat has been added to the system. Okay, its energy is increased. Heat is flowing into the system. Endothermic. Right. So positive means heat is flowing into the system. Q negative is exit. Okay. Thermic. I have an R someplace in there. Okay. I've decreased the energy of the system. Okay. Endothermic, I've added energy. Positive value of Q. Exothermic, negative value of Q. It all works out into the same case. Again, we'll always look at, did I add or remove energy from the system in the form of work or heat? Okay. So again, let's look at this problem. So again, delta E is equal to Q added to the system plus the work done on the system. Heat added to the system, work done on the system. So look at this problem. What do we say? So Q is going to be 15.6 kilojoules of heat that I added to the system. W is going to be 1.4 kilojoules that I added to the system. Q plus W is now 0, carry the 1, I get 17 kilojoules of energy. This is the change in the energy of the system. Change in the internal energy of the system is increased by, I've added heat and I've done work on the system. How did I add heat? Well, maybe I held a match to it, or I held a flame to it, and maybe I did work on the system by compressing it, but in doing so, I added energy to the system. Right, so there we go. Okay. We can do addition and subtraction. Good. Now, again, in the way that thermodynamics is formulated is largely in the language of steam engines. And of course, the reason is because when thermodynamics was formulated, that was the technological breakthrough of the time, the Industrial Revolution. And so it's very sometimes useful to always draw out what's going on in the form of a piston. And here's the cross section of your piston. Here's the cylinder. Here is the piston itself. I have a pressure on the piston. I have a force that's pushing on it, force, and this has a cross-sectional area of A. Okay, and there's a gas. Okay, now at equilibrium, there's a pressure pushing outward and a pressure pushing inward, and the pressure is force times area. Okay, pressure is force divided by area. Okay, is the pressure of the system. Force divided by area. Ouch. Or the forces, area times the pressure. And so, for example, if I move this piston by a delta H, okay, that's some amount of force that I've changed. The work that I have done is equal to F, the force, times delta H, force times distance, is equal to pressure times area times delta H, and that is a change in the volume, pressure times delta V. Okay, so work is equal to P delta V. Now again, this is the work done, and the question is this the work done on the system or the work done by the system? And this is going to be the case of the work done on the system. So again, this is the definition of work. So I have a change in the volume, and this is now the work. Okay, the work done to the gas. In this case, if I compress, right, V final is less than V initial, implies that delta V is less than 0. It's a negative quantity. W is a positive quantity. And I guess the reason, hold on, this is somewhat of a counterintuitive, because they don't have this sign here properly. The pressure, and the reason this is confusing is because the force, at least in terms of my diagram here, is pushing in that direction. There should be a negative sign here. Okay, the force is pushing in that direction. Okay, towards the negative that direction. So if I compress the system, I put force in that direction. Initial volume, final volume, I've done work on the system. So if I want to put this, I did work on, so I did the work on the system. I compressed it. Work is, so its internal energy, delta E, is going to be something greater than 0, right? Because I increased the energy of the system. I did work on the system and compressing it, its internal energy is now increased. Now, we have to have standards, and the standard unit of pressure is 1 atmosphere. So 1 standard atmosphere, okay, is the weight of 760 millimeters of mercury. So the way this is done is you have a column of mercury that comes around like this. It's open on this side, and it's got a vacuum on this side, and I push a column of mercury 760 millimeters above this level. So if I have a tube full of mercury, it's fully filled up to here. I break open an end. Mercury is going to start to flow until I have the atmospheric pressure pushing back down, forcing mercury back up. The weight of that 760 millimeters of mercury is equal to 1 atmosphere. Now, another way to approximate 1 atmosphere is also approximately 15 pounds per square foot. So if you want to think about it, if I have, is that 15 pounds per square inch? Okay, and sorry about that, 15 pounds per square inch. So if I have a little square, well, actually these little squares here are 1 inch right here. If I have one square like that, this is 1 inch by 1 inch. So I have a column of air. If you want to think about it, I have a column of air going all the way up to the top of the atmosphere on top of that piece of paper, and it's pushing down 15 pounds, roughly. Okay, not exactly, but this number that I have over here is the standard atmosphere. 1 atmosphere is 760 millimeters of mercury. That's the standard atmosphere at standard pressure and temperature. Okay, now, so you can use this idea to convert between joules and volume, okay, liter atmospheres. Okay, a useful conversion is that 1 liter times atmospheres, which is unit of energy, right? Because this is pressure times the volume. P times V is an energy, is equal to 101.3 joules. Okay, now joule, let me write that again, 101.3 joules. Okay, a joule is the energy of is to raise or to move an object of 1 kilogram to 1 meter per second is a joule. Okay, so if you have, for example, in this case I have here, this of a balloon that's expanding. Okay, and so in this particular case, I might have a balloon that starts off with some volume, 4 times 0.00 times 10 to the 6 liters. Okay, and I expand that upon heating to 4.5 times 10, 4.50 times 10. Start again. 4.50 times 10 to the 6 liters. Okay, by adding (1.3 times 10 to the 8 joules of energy. Now, the balloon expands at a constant pressure, and I want to calculate the delta E of this process. Okay, I added that much energy, but I've also expanded, and I have an outside pressure, P is equal to 1 atmosphere. Okay, So remember Q, so E, delta E, is equal to Q, the heat added to the system, plus the work. And the way I like to write this is equal to Q added to the system minus P delta V. Okay. Q added to the system we already have. P delta V is 1 atmosphere, and my delta V is equal to the final minus the initial 4.50 minus 4.00 times 10 to the 6 liters is equal to 0.50 times 10 to the 6 liters, and therefore my P delta V, V final minus V initial, right, is equal to 0.5 times 10 to the 6 liter atmospheres. Okay, and I need to multiply that then by 103, and I'll pull out my calculator that I have here, my old-fashioned calculator. I don't know if you can see that or not. Clear that out. What do I have? I have, let's say 0.5, enter 101.3 times is equal to minus 50.63 significant digits, probably says 50.7 significant digits, times 10 to the 6 joules. Okay, so therefore delta E, I'm going to add, so in other words, I expanded this, and I added a lot of joules into this. So I added 1.3 times 10 to the 8th, and then this little bit times 10 to the 6th, 10 to the joules. Is going to be pretty close to that number right there, because this is a very, very small number that I just added. Okay, so we can do this right here. So we can convert all of this stuff into the units. It's all worked out right here. 5 times 10.5 liters. Determining the work. There we go. Negative sign is expanding, doing work on the environment. And there we go. We convert everything into our 50.1 joules. There we go. Again, adding all of these things together. 1.3 times 10 to the 8th joules minus 5.1 times 10 to the 7 joules gives you 8 times 10 to the 7 joules. That's the amount of energy in the system, because you added energy, but then it cooled because, or it lost energy because of the fact that it did work on the environment to expand. Okay, so let's end here. Now, let's think about this. If I have an endothermic process that performs work, it depends upon do I have more work than heat or more heat than work, if energy is positive. So always, always, always go back to this base equation right here. Go back to this base equation. Heat added to the system, pressure delta V. So if you just simply remember this equation, then whether or not the sign of this thing is positive or negative doesn't matter, but this is always correct. This is always correct. Pressure delta V, heat added to the system minus P delta V, is always correct. This could be positive or negative depending upon the verbiage that's used in the problem. Work done on the system or work done by the system. I always like to go back and simply put it in Q, heat added to the system minus PdV, P delta V, work done by the system. So P delta V is work done by the system. Plus, okay, so depending on it's work done by the system. Okay, it's just simply remember this equation. And then if you need to go back, Q plus delta W plus W or Q minus W, well, this is a lot easier to me. This is easier to remember. It's because this is always correct. This is always correct. It doesn't depend upon which textbook you happen to be using. which I find to be, sometimes it's simply historical. Next time, I will talk about the concept of enthalpy, which is another state function, and it's derived, like I show here, and I will show you how this comes about, and we'll talk about the concept of enthalpy and its importance in chemical systems. And good luck, stay safe, and good luck on your exams. Get out of this escape. Where is this?